Hello everyone, myself Aasif Baig, Assistant Professor from Civil Engineering Department of Tulsiramji Gaikwad-Patil College of Engineering and Technology, Nagpur. Today we will see the introduction of Structural Analysis 2 and we will start with the very first unit of this, that is Kani's method. So before getting into the subject, we would see the scheme of teaching and the examination. Structural Analysis 2 is the subject from the 5th semester, which is having total 6 hours per week as a load, in which theory having 3 hours, tutorial having 1 hour, and the practical is having 2 hours load. This subject is having external marks paper of 80 and internal 20 marks, so total that is 100 marks. Minimum passing is 40 marks. Practical assessment is having 25 marks external and internal 25 marks, so total practical assessment is 50 marks, out of which 25 is the passing mark, and the question paper having the duration of 3 hours. This is the syllabus of Structural Analysis 2, in which 6 units are there. Unit number 1 deals with the Kani's method and 2 with the approximate method of Structural Analysis 1 of multi-storied frame structure. It is by the portal or the cantilever method and the moment distribution method. Unit number 3 deals with the column analogy method and application of two beams. Then this unit number 4 deals with the introduction of flexibility method. Unit number 5 with the strain energy method, and unit number 4 deals with the theory of photoelasticity. These are the references book which you have referred for the Structural Analysis 2. That is C.K. Wang, Intermediate Structural Analysis, S.P. Timoshenko, Theory of Structure, and similarly for Jain and Jay Krishna, S.P. Timoshenko, and Raleigh and Daly for Experimental Stress Analysis. These are the practical which is conducted under this Structural Analysis 2. Total 16 practicals are there, but minimum 10 practical we have to perform. Unit number 1 having of 26 marks weightage, in which question number 1 asked for 13 marks and question number 2 is asked for the 13 marks. The total 26 marks are there, 13 marks or 13 marks. So this is the introduction of the Kani's method. Kani's method of structural analysis is developed specially for the analysis of multi-story building. Kani suggested an iteration process of the slope deflection method. In slope deflection, the number of simultaneous equation to be developed is equal to the number of unknown joint rotation and the displacement. But the major problem was to solve those equations manually. The major drawback of slope deflection is eliminated by an iteration process. This Kani's method is also called as iteration method. To overcome that problem, Dr. Kani from Germany presented an iteration method based on the formulation of slope deflection method, especially for analysis of multi-story building. So begin with the fixed end moment of standard loading condition, as this is the very initial stage for solving the multi-story building, as to determine the fixed end moment. So for fixed end moment of standard loading, which is given in this figure. So very first is the central point load having P. So you can see the rotation on the supports A and B. A is having anti-clockwise rotation and B is having clockwise rotation, and the fixed moment at A is PL by 8. So rather, by writing only PL by 8, looking into the rotation of it, we can write it down minus PL by 8. Okay, and then rotation BA, fixed moment BA is plus PL by 8. So similarly, the various loading conditions are elaborated over here. For eccentric point load, which is having WAB square by L square, WA square B by L square, rather telling we can see P load. It consists of P, so PB square A divided by L square, PA square B divided by L square. For two concentrated load at same distance is minus 2PL by 9 plus 2PL by 9. For three concentrated load at a same distance, minus 15PL by 48 plus 15PL by 48. For UDL, the beam subjected to uniformly distributed load, it is minus WL square by 12 plus WL square by 12. Uniformly distributed load on a half of the span, it is minus 11 WL square by 192 and for fixed end moment BA, it is 5 WL square by divided by 192. For wiring load, it is WL square by 20 on fixed end moment AB, and from BA, fixed end moment BA is WL square by 30. For pyramid load, it is 5 WL square by 96 fixed end moment AB, and fixed end moment BA is 5 WL square by 96. So looking into the rotation of it at from A to B, it is anti-clockwise, so we can write it as minus, and from B to A it is clockwise, so we can write it as plus while taking into the consideration. Okay, so similarly these also are the some fixed end moment of standard loading condition. Now moving towards the analysis of continuous beam with fixed end by Kani's method. So this is the numerical which we have to solve for the Kani's method. Analyze the beam shown in figure by Kani's method and draw bending moment diagram. So the numerical is given for continuous beam having A and D support fixed and B and C are the continuous one. AB span consists of UDL of 10 kN per meter and having span of 5 meter, and moment of inertia is not mentioned here, so we have to assume that as moment of inertia 1. So moment of inertia is only I there. And BC having the span of 4 meter and concentrated load of 25 kN 3 meter apart from B. Moment of inertia 2I. Member CD is having the span of 5 meter having concentrated load 40 kN and moment of inertia is I. So begin with the very first step of this Kani's method, that is fixed end moment. To calculate the fixed end moment, there are 3 members, so there will be 6 fixed end moment. So fixed end moment AB is minus WL square by 12. So W is here 10 and length is 5. So this is minus 10 into 5 square divided by 12. So we are getting it as minus 20.83 kilonewton meter. Similarly, for fixed end moment BA is plus WL square by 12. So W is 10, again length is 5 and divided by 12. So we are getting it as plus 20.83. Now fixed end moment BC is consists of eccentric point load. So this is minus W into A into B square divided by L square. So W is 25, A is 3, B is 1 divided by L square. L is 4 meter. So we are getting it as minus 4.69. Now fixed end moment CB is WA square into B divided by L square. So W is 25, A is 3, B is 1 and L is 4. So we are getting it as 14.06 kilonewton meter. Now moving towards the span CD. So fixed end moment CD is minus W into L divided by 8, as the CD consists of central point load. W is 40 kilonewton over there and span is having 5 meter. So minus 40 into 5 divided by 8, we are getting it as minus 25 kilonewton meter. Fixed end moment DC is plus W into L divided by 8. So we are getting it as 25 kilonewton meter. Now this next step in the Kani's method is rotation factor. For the iteration process, rotation factor is required looking into the stiffness of a particular member. So for calculating the rotation factor, we require the relative stiffness of each member looking into the joint. So there are two joints B and C, and that each joint having the two members. So for which we have to calculate the rotation factor, and for calculating the rotation factor we have to draw a column of table of 5 column. So very first column consists of joint, second column consists of member, third column consists of relative stiffness, summation of relative stiffness, fourth column, and in the last column we have to finalize the rotation factor of each member. Now now how to calculate the rotation factor? So rotation factor is calculated by the equation minus 1 by 2 into relative stiffness of the member divided by sum of the relative stiffness at joint. So this is the formula for calculating the rotation factor. Now in the first column we have wrote joint B. Now second column having of member, so joint B having the member 2, BA and BC. Now relative stiffness of BA is given over. Now how to calculate the relative stiffness? How to identify the relative stiffness? If the far end is fixed or the continuous one, then the relative stiffness is I by L, and if the far end is simple or hinge, then it is 3/4 I by L. So B to A, if you are looking, then A is the far end, and in case of this, A support is the fixed one. So the BA relative stiffness is I by L. So value of I is 1 and value of L is 5. So it is I by 5. We are getting it as 0.2 I. Now second member of joint B is BC. If we look towards C, C is the far end. So far end is the continuous one. Hence it is again I by L. Now value of I on the span BC is 2I and value of L is 4. So it is 2I by 4. So we are getting it as 0.5I. So on the joint B, there are two member BA and BC having the relative stiffness 0.2I and 0.5I respectively. Now sum of these two value, we are getting it is 0.7I as a total relative stiffness at joint. Now to calculate this rotation factor, we have to calculate it as minus 1 by 2 into relative stiffness of the member divided by relative stiffness of total joint. So by putting this value into the equation, we are getting it as minus 0.14 as the rotation factor of BA, and rotation factor of BC is minus 0.36. So logically, if you have to see, if we sum this rotation factor, the sum of the rotation factor at any joint must be equals to minus 0.5. This is the check we have to do for any particular joint. Suppose there are 4 members. So for a joint, if there are 4 members, so there will be 4 rotation factor. If you sum that 4 rotation factor, the sum of that must be equals to minus 0.5. So this is the check we have to do. So minus 0.14 plus minus 0.36, we are getting it as minus 0.5. Okay. Now moving towards the second joint, that is C. C joint is having two members, CB and CD. So CB, if we look towards B joint, that is the B is the far end. So far end having continuous one. So the value of CB relative stiffness is I by L again. Now I of that CB member is 2I. So it is 2I divided by 4. That is the length of that member. So it is 0.5I. Now looking into the CD member, relative stiffness is I by L, as I by L is because D support is the fixed one. So it is again I is having 1I and L is 5. So it is I by 5, that is 1 by 5. So it is equals to 0.2I. If you sum this value, we are getting it as 0.7I. So total relative stiffness of that particular joint is 0.7I. Now if you put that value into this equation to calculate the rotation factor, we are getting it as the rotation factor of CB is 0.36 and CD we are getting it as minus 0.14. Now this was the second step in which we have calculated the rotation factor. So in the beginning, in the 2 stage, we have calculated fixed end moment, and the second one was the rotation factor. Now the main process is started over here, that is the third step, to calculate the final moment. So for to calculate the final moment, we required the rotational contribution values. That rotation contribution values is nominated as M dash values. So this, for calculating M dash value, we have to prepare figure number 3b. For figure number 3b, we have considered the same numerical as same figure given in the numerical, as A is the fixed one, D is the fixed one, and B and C are the continuous. So instead of drawing that support, we have drawn this diagonal. Now what this diagonal consists of? So on the above the line, fixed end moment AB is written over here minus 20.83, Fixed moment BA is written over here 20.83. Fixed moment BC is minus 4.69 above the line it is given. Now fixed moment CB is given 14.06. Fixed moment CD is given minus 25 above the line, and fixed moment DC is written above the line, that is 25. Now in this diagonal, if the joint is consist of 4 member, so these 4 diagonal boxes or the portions we have generated, we have drawn. So here only 2 members having there. For the joint B, BA is having rotation factor minus 0.14, which we have calculated in step number 2, which is written on this. Now joint BC is having member BC is having rotation factor minus 0.36, we have written over there. Now similarly rotation factor CB and the CD minus 0.36 and minus 0.14 respectively, we have written in the same way. Now this middle value, which is 16.14 and minus 10.94, is came from the calculation of fixed moment, sum of the fixed moment at particular joint. So sum of the fixed moment at joint we have calculated. So joint B is having 2 member BA and BC. If we sum the fixed moment at BA and BC, we are getting it as 16.14, which is calculated over here. So sum of the fixed moment at B is 20.83 minus 4.69 equals to, we are getting it as 16.14 kilonewton meter, and that value we have wrote in the center of that box. Now summation of fixed moment at C, we are getting it as 14.06 minus 25, we are getting it at as minus 10.94, which is written in the center of joint C. So this is the initial step of third stage, and that is the iteration process. Now in case of iteration process, we have to calculate the rotation contribution value. Now rotation contribution value at A and D will be 0 because there is no contribution factor, but BC, BA, CB and CD is having the contribution factor, and hence there will be rotation contribution value as well. So initially the rotation contribution value at all these members are 0, but as the cycle goes on increasing, this rotation factor, these rotation contribution values we are getting in the progressive way. Now starting with considering this value as 0, we have to calculate the rotation contribution value of BA, BC, CB and CD, which is elaborated in this table. Now this rotation contribution value is called as M dash value. So we have to calculate M dash BA, M dash BC, M dash CB and M dash CD. Now rotation contribution value for M dash BA, in the first iteration the far moment is 0. So for first iteration it is taken as rotation factor multiplied with, in the bracket, sum of the fixed moment at particular joint plus far end moment of contribution value and near end value of the contribution value, we are taken as it as 0. Okay, so we are getting it as minus 2.26. So it is minus 2.26, we have wrote over here minus 2.26. okay, then M dash BC is having minus 0.36, that is the rotation factor BC. Then 16.14, that is the sum of the fixed moment at joint B, and then plus 0, that means the rotation contribution value. So rotation contribution value at far end at the near end are 0, so we are taken it as 0. So we are getting it the value minus 5.81. So minus 5.81 we have wrote over here. So M dash CB is minus 0.36, that is the rotation factor of CB, into minus 10.94, that is the sum of the joint fixed moment at joint C minus 10.94, and minus 5.81 is over there. So minus 5.81 is the near end contribution value. So near end contribution value recently we have calculated in the previous step. So minus 5.81 we have to consider. So we are getting it as m dash value, m dash cb value is 16.03. The m dash cd value is rotation factor minus 0.14 into minus 10.94 and minus 5.81. So minus 5.81 we are taken it as far end value of contribution value minus 5.81, and near end value is 0 at joint D. So this is only minus 5.81 we have to consider. So it is 2.35. So here is the first cycle has been completed, in which we have gone through this calculation, and we have got this value as minus 2.26, minus 5.81, 6.03 and 2.35. And similarly we have to progress for the new step, that is new cycle number 2, and we have to carry on this iteration till the value become same. So you can see the cycle number 3 having the value 3.21, and below this cycle number 4 is having the value 3.22. So this similar value if we are getting, then we have to stop this process. Okay, so usually this process end up with the cycle number 4. So we need to any perform for the cycle number 5. Okay, so let's see the example of second cycle, that is iteration number 2. So iteration number 2, again for m dash bc we are getting it as fixed moment rotation factor at ba into sum of the fixed moment at joint B 16.14 plus 6.03. 6.03 is the far end moment at of rotation contribution, that is 6.3 at CB written over there. So 6.03 we have to consider. So we are getting it as minus 3.1. Now m dash BC is minus 0.36 into, that is 16.14 plus 6.03. So we are getting it as minus 7.98. Now m dash CB is 0.36 into minus 10.94 minus 7.98. We are getting it as 6.81. Now m dash CD we are getting it as minus 0.14 into minus 10.94 minus 7.98. We are getting it as 2.64. So as a cycle number 2 we got the value minus 3.1 BA. M dash BC we are getting minus 7.98. M dash CB we are getting 6.81, and m dash CD we are getting 2.65. And similarly we have performed cycle number 3 and cycle number 4 for taking the upgraded value of this m dash, or we also say this rotation contribution value. Now moving towards the final moment. So the final moment, we have to consider the final value of this contribution. So final value of contribution we are getting in cycle number 4. So cycle number 4 value we have to take minus 3.22 for BA, BC minus 8.3, M dash CB 6.93 and M dash CD 2.69. So for final moment MAB, for MAB the equation is fixed end moment plus twice of M dash moment of near end plus far end. So for MAB fixed end moment is minus 20.83 plus twice of near end contribution moment. So near end contribution moment of AB is A is for the near and B is the far end. So near end having A is value of contribution is 0. So we are taking it as 0. So minus 20.83 plus 0 minus 3.22, we are getting the answer minus 24.05 kilonewton meter. Then MBA we have to take 20.83, that is the fixed end moment BA, plus 2 into minus 3.22. Minus 3.22 is the value of MBA, that is 2 into minus 3.22 plus 0, that is the far end moment. A is the far end now, so having A value is 0, so it is 14.39 kilonewton meter. And similarly we have gone through MBC, MCB, MCD and MDC, and we are getting the value of MBC is minus 14.36, MCB 19.62, MCD minus 19.62, and MDC 27.69. So all these six from these six value we have to draw the final bending moment diagram. So MAB is minus 24.05, the rotation is clockwise, hence it is in the upward direction. So we have drawn in the upward direction, that is 24.05. Now at joint B, BA and BC are the same value. As this indicate the structure is in equilibrium, this is in statics. So the sum of the moment at joint B is satisfied over there, becomes 0. So MBA is 14.39 and MBC is 14 minus 14.36. Those are the very much similar values. So if you drawn that, the diagram will plot above the line. So this is 14.39. Now moving towards the MCB. So if you sum the moment MCB and MCD, this is also become 0, and this satisfy the equilibrium condition of summation of moment at joint C becomes 0. So MCB and MCD is 19.62. If you plot that line goes upward as the rotation is clockwise towards MCB and anti-clockwise towards MCD. So it goes upward. So this is 19.62 we have plot. And then the last one MDC, we are getting it as 27.69. If you plot this in the clockwise direction, the line goes above the baseline. So this is 27.69. we have joined all these points, we are getting the final fixed moment diagram, final moment diagram. So friends, this was the solution of continuous fixed beam by Kani's method. In the next lecture, we will see the analysis of frame by Kani's method. Till then, thank you very much.